In this lesson, we're going to learn about the determinant of a matrix, what it is, how to calculate it, and what types of problems it can help us solve. Let's get started. The determinant of a matrix is a scalar value or number that is calculated from a square matrix. It tells you important things about the matrix, like whether it has an inverse, how it transforms space, or whether a system of equations has a unique solution. The determinant can help find areas and volumes, as we'll see later on in this lesson. Determinants are also used in multivariable calculus and in linear algebra. We can think of a determinant as a number that summarizes the behavior of a matrix. Notice a determinant is only defined for square matrices, and though you can calculate the determinant for a square matrix of any size, we will stick to 2 by 2 and 3 by 3 matrices only for this course. There are several ways to notate the determinant of a matrix. Let matrix A be the 2 by 2 matrix, 3, 2, 1, 4. The determinant of A can be written as det of A, where the letter inside the parentheses indicates the name of the matrix. It can be written as A with these vertical bars. Note that although this looks like absolute value of A, it's actually notating the determinant. And finally, the determinant can be indicated with vertical bars around the entire matrix. Each of these notations can be used interchangeably. For this class, we will mostly use this one. Now that we know some of the basics, let's find out how a determinant is actually calculated. Let's use matrix A again. To calculate the determinant of A, we take the product of these two elements, 3 times 4, and subtract the product of these two elements, 2 times 1. The difference between these products is the determinant. In this case, 12 minus 2 equals 10, so the determinant of A is 10. Let's write this as a general rule that we can use for all 2 by 2 matrices. For any 2 by 2 matrix M, the determinant is equal to AD minus BC. Give this a try on your own. Pause the video and find the determinant of matrix B. The determinant of B is calculated by negative 1 times 2 minus 5 times negative 1, which is really negative 2 minus negative 5, or negative 2 plus 5, resulting in 3. So the determinant of B equals 3. Is that what you have? Great! Now that we know how to calculate the determinant of a 2 by 2 matrix, can I apply this same process to a 3 by 3 matrix? Well, let's take a look. Consider matrix M. When I try to apply this same process, I realize the product of the diagonals excludes several elements from the determinant. So, what do we do? There are 2 ways to find the determinant of a 3 by 3 matrix. The first is a bit longer, but you'll need to be able to use the same process in future lessons. The second way is more of a shortcut. I'll show you that in a bit. To find the determinant of a 3 by 3 or larger square matrix, I have to use something called cofactors. The cofactor of an element of a matrix is a helper value that includes 2 things: a minor matrix and a sign. Each of these parts is determined by the location of the element you are using. To practice finding a cofactor, let's return to matrix M. For this example, I'm going to use the elements in the first row, but you can do this process using any row or column and arrive at the same result. The location of element 1 is M11. So to find the minor matrix for the cofactor of M11, we're going to cross out the row and column of the element, meaning we cross out row 1 and column 1 to get the minor 2 by 2 matrix. 4, 5, 2, 3. Now, to find the sign of the cofactor of M11, we take -1 raised to the power of 1 plus 1, since this element is in the first row and first column. -1 to the second power is +1, so this cofactor will be positive. In 3 by 3 matrices and larger, we can use a checkerboard pattern as a shortcut for determining the sign of a cofactor. Starting with the top left element, we note above each column alternating signs starting with positive. So in a 3 by 3 matrix, this is positive, negative, and positive. Since we have both pieces of the cofactor of 1, we will calculate the determinant of its minor matrix using the same process we used for a 2 by 2 matrix. 4 times 3 minus 2 times 5, which is 12 minus 10, which equals 2. The sign of this cofactor is positive, so this stays positive 2. Remember, we're trying to find the determinant of matrix M. In order to do that, we need to repeat this same process to find the cofactors for the remaining 2 elements in row 1, 3 and -2. Once we have the remaining 2 cofactors, we'll use them to find the determinant of M. Let's find the cofactor of M12. First, find the minor matrix by crossing out the first row and the second column. That leaves us with the 2 by 2 matrix 0, 5, 1, 3. Calculate the sign by raising -1 to the 1 plus 2 power, or -1 cubed, which is -1. Remember, we could also use our checkerboard, which will also show us the sign is negative for cofactor M12. Finally, calculate the determinant of the minor matrix, 0 times 3 minus 5 times 1, which is -5. Since the sign of the cofactor is negative, we need to multiply the determinant by -1. So -1 times -5 means the cofactor of M12 is equal to 5. Pause the video to find the cofactor of M13. Then come back to use all of our cofactors to calculate the determinant of matrix M. I found the cofactor of M13 by crossing out row 1 and column 3, leaving me with the minor matrix 0, 4, 1, 2. I used the shortcut to determine that the sign of the cofactor of M13 is positive. So I calculate the determinant of this minor matrix by taking 0 times 2 minus 4 times 1, which gives me -4. Since the sign of the cofactor is positive, that means I multiply by +1, which just leaves it as -4. Now that we have all 3 cofactors notated with this capital C and the location of its element, I'm ready to calculate the determinant of the matrix M. I use the row I expanded, 1, 3, -2, and multiply each element by its cofactor, then add the results. I get 1 times 2 plus 3 times 5 plus -2 times -4. Simplify to get 2 plus 15 plus 8, which equals 25. So the determinant of M equals 25. Pause the video now, review your work from this example, and summarize these steps in your own words. When you come back, we'll summarize the steps together. To find the determinant of a 3 by 3 matrix, we select a row from the matrix and find the cofactor of each element in the row. This involves finding the minor matrix and its determinant, and then finding the sign, positive or negative. Next, we multiply each element from the selected row with its cofactor and add the products together to find the determinant of the 3 by 3 matrix. In math words and symbols, It looks like this. The determinant of any square matrix, n by n, is equal to the sum of the products of the elements and their cofactors for one row or column of the matrix. Since we're only working with 3 by 3 matrices, our definition can be written like this. If you feel ready to try this on your own, pause the video and find the determinant of B. If you'd like to follow along with me, just keep watching. The first thing I'll do is find each of my cofactors for the elements in row 1. Again, this process will work for any row or column. C11 has a minor matrix of 0, 6, 1, negative 3, which I found by crossing out the first row and first column of matrix B. I also know C11 will be positive using the checkerboard shortcut. The determinant of the minor matrix of C11 is negative 6. C12 has a minor matrix of negative 2, 6, 5, negative 3, and its sign will be negative, meaning I will multiply the determinant by negative 1. The determinant is negative 24, so negative 24 times negative 1 is positive 24. Finally, C13 has a minor matrix of negative 2, 0, 5, 1, and its sign is positive. The determinant of the minor matrix is negative 2. Now that we have all 3 cofactors, we will multiply each by its corresponding element. 3 times negative 6 plus 2 times 24 plus negative 1 times negative 2 is 32. So the determinant of matrix B is equal to 32. Hopefully, by now you agree this process isn't too difficult. But are any of you wondering about the shortcut I mentioned? I thought you might be. Let's keep using this matrix B from our last example. The shortcut for finding the determinant uses a similar approach to finding the determinant of a 2 by 2 matrix. And it does this by copying the elements from columns 1 and 2 and writing them on the end of matrix B like this. Once we've written this extended version of matrix B, we'll first find the product of the elements along these 3 diagonals. Here, here, and here. 3 times 0 times negative 3 is 0. 2 times 6 times 5 is 60, and negative 1 times negative 2 times 1 is 2. Next, we're going to do that same thing but with these 3 diagonals. 5 times 0 times negative 1 is 0. 1 times 6 times 3 is 18, and negative 3 times negative 2 times 2 is 12. Finally, to calculate the determinant of B, we'll subtract the sum of the numbers in the purple box from the sum of the numbers in the orange box. 60 plus 2 is 62, and 18 plus 12 is 30. So, 62 minus 30 is 32. Well, look at that! We got the same answer as before. What a neat little shortcut! Pause the video and use the shortcut method to find the determinant of matrix C. I start by adding on my 2 extra columns, like so. Then I find the products along each set of diagonals. I get negative 8, 0, negative 18, and negative 12, 10, and 0. Next, I need to add each group together. Negative 8 plus negative 18 is negative 26, and negative 12 plus 10 is negative 2. Now to find the determinant, I subtract negative 2 from negative 26, and I get negative 24. Is that what you had? Awesome! Now let's look at some ways we can apply the determinant to solve other problems. As I mentioned at the beginning of this lesson, determinants have many applications in advanced mathematics, particularly in subjects like linear algebra and calculus. But matrices can also be applied to a familiar study of mathematics, geometry. In coordinate geometry, meaning figures in the coordinate plane, we can use matrices to represent shapes by their coordinates, which can then be scaled or transformed with basic matrix operations. In this lesson, we will look at how the determinant can be used to find the area of a figure. We'll start by looking at a parallelogram. To define our parallelogram, we'll actually use a concept you just learned about in Unit 7, vectors. You might recall from Vector Operations Part 1 that when you add or subtract vectors, you can use what's called the parallelogram method. This involved placing the initial points of both vectors on the origin, like this, then translating a copy of each vector to the end of the other vector to create a parallelogram. For our purposes, we're going to use the same concept of a parallelogram created by two vectors. First, we need to identify the component form of each vector. Do you remember how to do that? Since these are position vectors, their component forms are simply the coordinates of their terminal points. So this red vector has component form 2, 3, and the blue vector has component form 3, 1. Next, we can find the area of the parallelogram formed by these two vectors by calculating the determinant. Oh, but wait, we don't have a matrix. Before we can calculate the determinant and find the area, we need to represent our vectors in matrix form. As you saw at the beginning of the unit, vectors can be represented in a matrix as either a row or a column, and it can simplify operations, which you will see in just a moment. Let's write our vectors as columns, so 2, 3 becomes the column 2, 3, and 3, 1 becomes the column 3, 1. Conveniently, when we combine our columns, it creates a 2 by 2 matrix, and we can easily find the determinant. 2 times 1 minus 3 times 3 equals 2 minus 9, which is negative 7. Since we're calculating the area, we know our answer cannot be a negative value. So what should we do? We'll take the absolute value of the determinant, making the area equal to 7. If you're wondering why this works, I've included an extension activity of this proof in the lesson activities for this lesson. You should check it out. So, we know we can find the area of the parallelogram using the determinant. But what about other figures? Let's look at this example. Find the area of triangle ABC with vertices 2, 3, 0, 0, and 3, 1. How could we apply a similar process as before to find the area of this triangle? I'm going to start by looking at these points in the coordinate plane. It seems to me the easiest approach would be to write side AB and side BC as vectors and just find the determinant like we did before. But do you see a problem with this approach? Right. The determinant with two vectors gives the area of the entire parallelogram. So, is there anything I can do to find the area of the triangle? Well, the area of the triangle is exactly half the area of this parallelogram. That means if I find the determinant, I can just multiply by 1/2 and find the area of this triangle. Since this example gave us the coordinates of these vertices, let's look at how we represent those as a matrix. Just like with vectors, the vertices each become a column of our matrix. This leaves us with a 3 by 2 matrix. But we need a square matrix, so we'll add a third row of all ones. This will allow us to calculate the determinant without changing any of the values because we're multiplying by 1. Since this is a 3 by 3 matrix, I'll choose to apply the shortcut method. 9 minus 2 is 7, which I'll multiply by 1/2 to find the area of the triangle to be 3.5 units squared. Believe it or not, you now have the skills to use the determinant to find the area of any polygon. Really! For instance, Consider this quadrilateral or this hexagon. How could we apply the same process to find their areas? Since we know how to find the area of a triangle, we can split any polygon into smaller triangles. Find the area of each triangle and then add them up to find the area of the figure. You'll get to practice this in your lesson activities. Let's summarize the steps we use to find the area of a figure before we finish up for today. First, we create a square matrix with vector components or coordinates, depending on the information we're given. If your matrix isn't a square matrix, you can make it square by adding a row or column of all ones. Next, find the determinant of the matrix. If you're finding the area of a parallelogram, its area will be equal to the determinant. If you're looking for the area of a triangle, you'll divide the determinant by 2. In this lesson, you learned how to find the determinant of a 2 by 2 matrix. You also learned 2 methods for finding the determinant of a 3 by 3 matrix. We then put the determinant to work, using it to find the area of a parallelogram and triangle. You'll see in upcoming lessons that the determinant is a powerful tool that can be used to solve many types of problems. Make sure to complete your notes and lesson activities before moving on to the online practice. See you next time!